I guess while we wait, are there any questions from last time? No. 30 seconds.
Should there have been a factor of 2?
I'm working in conventions where 2 is equal to 1.
That makes sense. But what if it's 2 to the end?
Also. What? Yeah, the one with the hat?
No, it was
one with the
related
glass.
to Mary.
Ah, okay.
Yeah, she was working with Andy.
With Andy, okay.
Yeah, on his BMS stuff.
Ah, okay, I see.
Yeah, she like
No, it was something else.
worked like
Mm-hmm.
yeah, and I told her about the radiation.
Oh, okay, yeah, yeah. Right. Okay, go on. Yeah. Okay, so we are ready to start. So I'll continue the discussion we were having last time. So last time we noticed that we could take the SYK model and up to these replica corrections, which go like 1 over n to the q, we could replace it by an integral, functional integral over some variables, sigma tilde and g tilde, and then some action which had an overall factor of n, and then was some factor of sigma tilde and g tilde. Right? So this gives the partition function, and if we wanted to calculate something like a 4-point function, so for example, a 4-point function of the form psi I of t1, psi I of t2, psi j of t3, psi j of t4, and for the sake of the argument, let's imagine we are summing over the indices I here and also over the indices j. That integral will be given by, so here we don't have the fermions explicitly, but we can compute things like this that have the sum over indices by replacing, remember that one of the equations of motion was setting this equal, well, there was a delta function in the functional integral that was setting this quantity to g tilde, okay? And then we remember the change of variables, so we started from the functional integral for the fermions, and then we introduced the variable g tilde, which was equal to this quantity, and that equality was enforced by the integral over sigma, right? And then we had some action. Then we could integrate the fermions, and we had some effective action in terms of sigma tilde and g tilde. So that means that we can do this integral by doing the functional integral, the same functional integral we have here. And now here we put just g tilde of points 1 and 2, and g tilde points 3 and 4. Right? These are the two arguments, the two times that are the arguments of the g's. And then we have, well, the action, minus the action of sigma tilde and g tilde. And in principle, the leading order computation here is given by putting the classical values here for the classical solution, and that just gives us the disconnected answer, right? The disconnected, that gives us a product. So this is the leading order answer, is g of 1 and 2. G of 1 and 2 is the classical solution, and then 3 and 4. And then if we want to calculate corrections, we have to do the functional integral for fluctuations around this the original solution. So we take so we have the action s. Let me call it x0 of g and sigma. This is the action on the classical solution, and then we expand this to quadratic order in g and sigma and so on, and then we have some fluctuations of g and sigma, both g and sigma of this type, and then we need to integrate them out, and in that way we generate the correction. And because there is an n here, once we do that integration, we'll get a 1 over n. So the answer here will have a 1 over n, and then there will be here some function of the 4 times that we get by somehow inverting this operator. And that, in principle, can be done. However, there is at low energies, so this can be done, and can be done for any value of beta and j, so for any value of the temperature. But now we are going to start discussing some aspects when beta j is much bigger than 1. And in this regime, we have seen that this action has some 0 modes, almost 0 modes, right? So in the space of g's and sigmas, we have, so these are the g's and the sigmas, and we'll have some manifold of low action solutions. And so we can, because those, and we can parameterize the action along this line. So the full action only along this valley, we can parameterize this as a function of f, which is f is a coordinate that takes us, it's a reparameterization, but it moves us along this valley. Okay. And we have this action which, well, n times f was n times alpha over j of the Schwarzian derivative of f tau. Okay. So we have this action. And so this action, this is just, so there was the classical solution, and this is just the action along this valley. It's and for large j, this is a smaller. This action is smaller than the values of the action in these directions. So when we integrate things out, so when we integrate this f out, we'll get an answer here that will be enhanced relative to the other terms. So the integration along these directions will give us here some functions of the times which are of order 1, right? And then the integration of this piece will give us a bigger factor that will be enhanced by a factor of j. Okay, so it's this j, and then by dimensional analysis we'll have, let's say, a factor of beta, and then we'll have here some function of the ti's over beta. Okay, so the pieces. So this piece will be essentially independent of j, right? So there will be functions of the times divided by beta, dimensionless function of this kind, and it can be computed using techniques of conformal symmetry and so on. And then this piece is bigger and is given by doing the functional integral only along this valley. Okay, so that functional integral is given by, so we have to change the measure first to integrate along the orthogonal directions and then along this direction. So there is some measure for integration for f, and then here we put the gf 1, 2. Remember, gf is just a reparametrization acting on the classical solution. So we had the classical solution, which was a simple scaling law, and then we have this reparametrization acting on it. And in this, so this is a function of f, and then we have a similar thing, function of f, and then we have this action. So e to the minus n over j. There are some coefficients here I'm not writing. The Schwarzian derivative, and if we put the signs right, there is a plus here. So that's that's what we would like to compute, and we can do this, and we if we are doing it in the context of perturbation theory, so in the context of a 1 over n expansion, we can further expand this action around the classical solution, and then fluctuations around the classical solution. So the classical solution for the finite temperature configuration was something like tangent, this is in Euclidean space, tangent of tau over beta, maybe a pi here. And now, small fluctuations, we just add an epsilon of tau. And then we can expand that action. And so I'm going to come back here and simply say that the expansion of this action contains terms which are minus epsilon double prime squared minus epsilon prime whole squared. Okay. We mentioned that last time. And then this is a quadratic action. We can also expand these pieces and then find the answer. And that will give us the 1 over n. That will give us this term. Okay. This is not too complicated. I'm not going to do it explicitly, but it can be done. Okay. So an important feature of this action is that it contains here these classical solutions, which go like a constant, or like e to the plus or minus I tau in Euclidean signature, which when you continue to Lorentzian signature goes like e to the plus or minus t. Okay. And it is these terms that are related to the growth, to the chaos behavior in the chaos regime. So these terms are, if we are doing the Euclidean functional integral, we mentioned last time that we could expand this in Fourier series, and then we do the integral over each Fourier mode, and we do not include in those integrals these 3 Fourier modes. Okay. But nevertheless, it is possible that so when we consider a correlator, especially a long-time correlator, which is involves long-time separation, so we can think of, for example, there is we take the first G1, 2. Let's say this is at 1 and 2. We'll have some sources for the epsilon, and we can think of this as sourcing some classical solution for the epsilon that then propagates at later times and then is measured by, let's say, points 3 and 4. Okay. Now, if this source is some classical solution for the epsilon, this classical solution might contain or not these terms, but because these are SL2 reparametrizations and 3 and 4 is a G which is SL2 invariant, we will not get anything that grows in time with this configuration. Right? But if we have another configuration where in Euclidean time the points are ordered in this way, we might get some more non-trivial contribution that is associated to these zero modes. Let me try to explain how that happens more in Euclidean signature and how it's related to the chaos discussion. So we've seen that in order to see the growth of the commutator, it was enough to understand the decrease of a particular out-of-time order correlator. Right? So we need to compute out-of-time order correlators. So out-of-time order correlators are given by correlator, which in Lorentzian signature. So those were Euclidean signature contours. So now we are in Lorentzian signature. So we want to insert an operator here. So this would be operator number 1. This would be operator number 2. And then we want the 3 and the 4 to be in this way. So we have 2 at, let's say, time equal to 0, 2 at time equal to t. But they are ordered in such a way that we have to go backwards and forwards in time, okay, to compute this. And then, of course, we could join these two by going some displacement beta here. We introduce the temperature here, and we connect these two. So in the functional integral, we're not supposed to integrate over the overall SL2R0 mode. But here, what can happen is that these two are sourcing a relative SL2R transformation between these two parts of the contour and the other two parts of the contour, right? So this and the one that goes in temperature back to here, right? So if that happens, then there could be so these two shift these two contours by this SL2R transformation, so they create a solution which differs between here and there by an SL2R transformation, and it can lead to an exponential, well, some exponential deviation for the formation for these 2 points. And then, yeah, I guess I'm not explaining this clearly enough. Let me be a little more clear. So we're trying to approximate the functional integral, okay? So we are going to think about it the following way. So we start with some state for f, okay? And then we're going to, let's say, think of these two as a source for fluctuation, right? So first epsilon was 0. Now epsilon is not 0. Now in these regions, we'll get some source. This is some, let's say, term in the right-hand side of the equations of motion. So we can think of these couples linearly to epsilon, and we can think of, so this is the usual type of Green's function calculation where we, here this will expand to linear order in epsilon, and so this will source, this will be like a source in the right-hand side of the equations of motion for epsilon. And then we can have here an epsilon which contains, it will be the classical solutions, and the classical solutions involve the, there are 4 classical solutions to that equation. These are 3 associated with SL2R 0 modes, and there is one that is linear in T that is not important for our discussion. And so we source those solutions, and there are 2 in particular. There's a particular one that grows exponentially in time. Okay. So it grows exponentially in time, and so the epsilon here grows exponentially in time, and it will display it when we get to points 3 and 4. What we're going to do is we're just going to evaluate this this function on those on the classical solution that we got by solving the equations with the source. Okay. Evaluating this means taking the original function and doing the transformation given by this f. Okay. So this f is a particular transformation that is displacing point 3 away from point 4. Okay, because we have an exponentially growing reparametrization of this part of the contour relative to that part. It's not an overall reparametrization. It's just a relative transformation of this part of the contour relative to that part of the contour. Okay. And for that reason, then we'll get that the original function is that function of 4 times. When we evaluate it, so let's say these 2 times are 0 and these 2 times are t, we'll get that it will go like e to the t. Okay, where this t is the t in units of 2 pi beta. So this is when when beta is 2 pi, and if beta is not 2 pi, we have just this. Okay, so that is an explanation for why we get this exponentially growing piece. Okay, and why the Lyapunov. So this is the Lyapunov exponent lambda, right? So let me be a little more clear. So we have the 4-point function is equal to a product of 2-point functions times 1, and then there are some corrections, and the corrections go like 1 over n, and then they're enhanced by a little factor of beta j, and in addition it grows in time with this factor. Okay. And this is a piece that we can get from the Schwarzian action. It contains other pieces which are not growing exponentially in time, other 1 over n pieces. And then there are further, of course, corrections. Okay. So this is a derivation for why this model is giving us the maximal Lyapunov exponent. And it comes from the pattern of symmetry breaking. So the fact that we had this emergent reparametrization symmetry, and the fact that it was slightly broken. Okay. Okay.
Sorry.
Yes.
Yeah, they didn't follow you. Okay.
Yes. How to get this formula? Well, you take this action, you approximate it this way. You take the correlator 1 over t12, right, to the 2 delta. You reparametrize it by this function. Okay. You expand to linear order in epsilon, here and here, and you do this functional integral. Okay, you will get that answer. I didn't explain why you get that answer, but what did I do? Well, yeah, this was the okay, yeah. f1 minus f2, let's say, and then we put this particular f, we put it here, and then we'll have to reparameterize, put in f1 prime, f2 prime to delta, right? So we're just, we put this expression here with that particular f, right? Is that clear? And then we expand this whole thing to linear order in epsilon. So it's just something relatively simple you get here. And then you do this functional integral, and you get this functional integral in Euclidean time, and then you have to continue to Lorentzian signature, right? And when you continue to Lorentzian signature, you have to order the points in Euclidean time in some particular way, so as to, the order of the operators in Lorentzian signature depends on the order that they had in Euclidean signature, right? So if you want to put them in this out-of-time order form, you have to order the points essentially like this in Euclidean signature. First one, then three, and so on. And so you do the functional integral, and you get some answer, and the answer goes in that way. Okay, so that's the mathematical. I explained the mathematical procedure. That's the mathematical calculation. Okay, it might seem mysterious that we get that answer at this point, and then I try to give an explanation for why we get this answer. Okay, the explanation for why we got this answer is that we think of this calculation. This is a typical Green's function calculation that we can think of. You perturb the classical solution, which was initially 0. You act with a little source, which is one of the points, and then you solve the equations of motion, and then you evaluate the second appearance of epsilon. So first appearance of epsilon is the one that appears here, right? It acts as a source for the equation of motion that you get from this action, right? It's a fourth order equation. So there will be these 4 solutions for linear independent solutions. One of them is growing, okay? Then you evaluate the action you get here on this solution. Okay, if you take the epsilon that appears here, there will be an epsilon evaluated at 3 and an epsilon evaluated at 4. Maybe there will be some epsilon 3 prime, etc. And so linear combination of these things. And you evaluate on that solution that is growing in time. Okay, and that's why you get this growth in time. Okay, is that not clear? I will present a slightly different version. It's a little more geometric when we talk about ADS2, which I think probably I should talk right now. I think it will become a little more clear when I give a more geometric picture of what the Schwarzian means in ADS2, and then it will become a little more clear. So the point I want you to get here is, number one is that this behavioral late times is dominated by the Schwarzian action, and it follows from the pattern of symmetry breaking. And second, that the particular exponent we get here is associated to the fact that we had these SL2R 0 modes. Okay. And because of the geometry of the group, the geometry of SL2R, we got these particular exponents. Yeah, perhaps I didn't explain this properly now. It will become a little more clear in a second. Well, maybe. Well, you can do as an exercise that if you take this f, which is tangent, and do an SL2R transformation of f, right, with small, which is close to the identity, and then you try to reproduce whatever you get by changing this epsilon, right, you'll find that the epsilon is associated to SL2R transformations are these two. So exercise. So that's an exercise, right? So let me exercise. Take f to af plus b over cf plus d, right? When b and c are very tiny and a and d are very close to 1, right? So you expand this. So this is this will give you the original f plus some delta f, right? And then you match this delta f with a similar delta f that you get by taking this expression and changing epsilon, right? So this should be equal to somehow d of this f times d epsilon, and then some change in epsilon. And you will see that the delta f's that you get correspond to epsilons that are of these 3 forms, one for each of these terms that you can change here. Is that clear where this came from? Yeah. So it came from the geometric action of SL2R. Okay. So now, good. So now what we're going to do is we're going to talk about ADS2 gravity. So first, we're going to try to put this in context. So in general relativity, in any number of dimensions and so on, we can have black holes, right? These black holes sometimes can have charges, let's say angular momentum or electric charge, for example. Let's say it has electric charge. Then you typically find that the mass has to be bigger or equal than the charge in order to have a reasonable solution without naked singularities. This is in some units of measuring the charge. Then you find also that when the mass goes to the charge, so you saturate this inequality, typically you find that the geometry develops an ADS2 region. The Hawking temperature goes to 0. Okay. So, and the geometry roughly looks like this. So this might be a black hole in R4, for example. And then in this, so here we had R, let's say 3, 1. Then here, this geometry here becomes ADS2 times S2. Okay. So it develops a long neck with geometry of a two-dimensional anti-de Sitter space. And this two-dimensional anti-de Sitter space has some kind of scaling symmetry that corresponds to getting closer and closer to the horizon. Okay, so we get some scaling behavior when you go near extremality. It's a bit like the scaling behaviors you get in condensed matter physics when you approach a second-order critical point. Okay, so now what we like to be interested in is to describe the physics at extremality or very close to extremality. So the case m equal to q is called an extremal black hole, and m close to q is near extremal black holes. So let's first do a naive approach. So we say, well, we have ADS2, so what could be gravity in ADS2? Could be just simply an action which is like this. So we have a two-dimensional action. So we integrate d to x, square root of g times r, and then we'll have some coefficient here. I'm going to call it phi naught. And the coefficient comes from, for example, the area of the sphere. So if we come from 4 dimensions, we have the 4-dimensional curvature. We have the area of the sphere in Planck units. So we'll that will be phi naught. Okay, so this is our first candidate action. And this candidate action has a nice feature, which is that if you consider this in a, well, we don't go all the way to extremality, but we consider kind of finite temperature configuration where this has a horizon. Then the Euclidean black hole solution, you can evaluate it on this metric. And this action is topological invariant, so it gives us a topological invariant of the two-dimensional metric of the r and t directions, which is like a cigar. And that's the same as the topological invariant for the disk. So it's some factor of 2 pi or 4 pi or something like that. And so that gives us the entropy. So it gives us the, let me call it S0, which is the actual entropy, which is proportional to this phi naught up to, well, there are some numerical factors which in the end give the area over 40 Newton. Okay. So that's good. But we'll also like to describe some near extremal properties. So we'll also like to be able to describe, let's say, particles propagating here, and maybe if we have Hawking radiation or not, and so on. So we want to understand some aspects of the dynamics of the system. And the problem is that this action, due to the fact that it's topological, does not give any non-trivial gravitational dynamics. And furthermore, if we think that we have this action for gravity, right? So if we have this action plus, let's say, some action for matter, which contains, well, it has this metric, and let's say a bunch of fields that propagate on this metric. So this is the first-order naive approximation. And if we only have this approximation, then when we calculate the equations of motion for the metric, this term is topological, doesn't contribute anything. And this term would set the stress tensor of matter, so T matter mu nu, we would set it to 0. Right? So that would be the equations of motion for this metric. So that is too constraining. I mean, it's just setting that we cannot excite this space. Okay, so that's a feature. Now, this feature is, in some sense, reasonable to expect, because if we thought that this system had a quantum mechanical dual that has exact SL2R, exact scaling symmetry, then the density of states in that dual, well, first of all, we expect it to be finite because the entropy is finite. But the density of states that are consistent with conformal symmetry could be either delta of E, or let's say 1 over E, just this is by dimensional analysis. And in this case, we shall only have zero energy states. And in this case, we have something that diverges at low energies, which is where the scaling approximation should be better. So in both cases, well, this case is wrong because it gives an infinity, so it's bad. And in this situation, we are not free to excite the system, which is what we would like to do. So we might consider a gravity like this in ADS2, and might be good for counting the entropy or the number of states at exactly zero energy. And it's been used for this purpose, but it cannot describe the feelings of an observer inside ADS2. It doesn't allow an observer inside ADS2. So the thing to do is to modify this action slightly and say that we had that term that we liked. We liked some aspect of this term, which is that it reproduces the extremal entropy. And then we're going to add a new term that has the form square root of G phi R plus 2. And then we also have that S matter of G and chi. Now, this phi field, you should think of it as keeping the leading order deformations away from the extremal limit. So in the extremal limit, the sphere has a particular size. But when we are near extremal, the sphere starts growing a little bit towards infinity. And this phi is somehow the value of the area of the sphere minus the extremal value, which was phi 0. Okay? So the total area of the sphere is 5 plus phi 0. Okay, so we are going to consider this action. This particular term is called the Yakib-Teitelbaum term. Was also considered by Armeri and Polchinski. And it's a kind of simple theory of gravity. And in fact, this is the most this is the generic situation around ADS2. So let's consider a so the following is true. So if we consider a spherically symmetric gravity theory in 2 dimensions, so we'll have some term. In general, we'll have terms that go like, let's say we have some function of some field, right, times R. So this is in 2 dimensions. This is true for any spherically symmetric reduction of gravity, what I'm going to say right now. So we can have a term like this. We can have a term that goes like B times phi. And we can have some terms that go like C of phi times gradient of phi squared. Right? So this is the generic spherically symmetric reduction of gravity. So we have some field that appears multiplying R. And that same field could appear without R. And it could appear also with this gradient. So that's the generic situation. And we can do here, we have the freedom of 2 field redefinitions. One is that we can field redefine phi by an arbitrary function of phi. And the other is that we can multiply the 2-dimensional metric by another function of phi. So we have 2 functions, 2 functional degrees of freedom by field redefinitions. So by field redefinitions, we can just define whatever appears here as phi. Okay, that's one of the field redefinitions. And then we're left with these 2. And then we can do another field redefinition of the metric that somehow gets rid of this term. So then we have this, and let me call the one that appears here as U, conventionally called U. So that's a generic situation for spherically symmetric reduction. Okay? Now, if you want the solution to be close to ADS2, then this U has to be linear in phi, and the coefficient sets the radius of curvature. There are other things you can do. You can take this U to be other things, and then they describe other spherically symmetric reductions. I mean, you can have the spherically symmetric reduction of the Schwarzschild black hole, for example. That would correspond to some particular U of phi. Okay. So what I'm trying to emphasize here is that this is completely universal for any near extremal black hole. Okay, that's the correct description for any near extremal black hole. And now we had this issue when we calculate the equations of motion for the metric. And now instead of having this, we'll have also some kind of stress tensor that we get from phi. So we take derivatives with respect to the metric. We have a kind of stress tensor for phi. So let me call it d phi mu nu. And this stress tensor for phi has a bunch of derivatives. So it has the form of, roughly speaking, second derivatives acting on phi plus some other combination of second derivatives. And it basically sets the value of phi in terms of the stress tensor of matter. Okay. Okay. And in particular, in the case that there is no matter, so we get so if this is 0, then we get some equations which well, I'm not writing completely explicitly, plus some other term of order phi. I'm not writing all the coefficients correctly, equal to 0, and there is a solution to this. So, well, one solution is 0, but we're not interested in the solution that is exactly 0, because but if phi has some value at the horizon, then okay. Before doing that, let me just point out something. Let's look at the equations of motion for this metric. So the equation of motion for phi sets r equal to 2 and gives us a metric which is exactly the ADS2 metric. So in Euclidean space, that would be a metric that goes like d rho squared plus sinh rho squared d tau squared. Tau is the Euclidean time. And then if we vary the metric, then we get an equation like this, and whose solution is phi equal to the value it has at the horizon times cos of rho. And this is essentially the unique solution up to an overall constant here. So phi is not a dynamical field. This action has, in some sense, no dynamics. It's basically pure constraints in 2 dimensions. And this agrees with the fact that we don't have gravitons in 2 dimensions, because there are no transverse dimensions, right? Or you don't have spherically symmetric gravity waves in higher dimensions. Very good. Okay, so that's well, this is a straightforward analysis. Now we'll do a slightly more sophisticated analysis. We are going to ask ourselves what are the asymptotic symmetries of ADS2. Okay. And this makes some connection with other things. We'll resonate with some things. So asymptotic symmetries are symmetries which preserve the asymptotic form of the metric, but do not preserve the whole form of the metric. Okay, only the asymptotic form of the metric. So, for example, the metric very far away goes like e to the 2 rho d tau squared, right? Plus well, d rho squared. So the leading factor that is very big is this factor. Okay, and so this has a following symmetry. So if we change tau to some function of tau, right? And at the same time we change rho to rho minus logarithm of f prime, right? So if we do this change, then we see that so here we will get an f prime, but after we do this shift, we cancel that f prime, and we get the same form of the metric, right? The asymptotic form of the metric essentially remains constant, and we can adjust this a little bit so as to keep the leading order term here also invariant. Okay. So this is what's called an asymptotic symmetry, and people have studied asymptotic symmetries a lot in flat space, in ADS, etc. And in this particular case, ADS2, we have this infinite dimensional group of asymptotic symmetries. Okay. So any situation that has the symmetry will have this. Say again. Yes. Yes. Yes, you can take this. Yeah, that's right. Well, I mean, you can view that infinite line as the limit of a well, if you think of the infinite line, you allow these transformations that are singular, that have some singularities. Like that transformation, for example, has singularity at some point. And so if you want to deal with a space that is a little more nicely defined, you would take functions which are, so you would work in the picture here that we are working here right now, where tau is compact. and then the functions are periodic and have no singularities. Okay. So if you want to think, so that line is something that is useful. So you could work completely at the level of the circle. Thinking about the line is, if you wish, an approximation that is particularly useful. It has just a slightly simpler form for the SL2R transformations and so on. And in addition is some limit where you take the actual physical value of the size of the circle to infinity. I'll discuss what the physical value of the size of the circle is in a second. So for the time being, I'm not saying anything about it. Okay, so that's the asymptotic symmetry. And there is one, and we are changing the bulk metric. So one way of thinking about this is the following. So we have ADS2, okay, and it will be important for us that we'll put a boundary at some location that we'll discuss later, and we fix the metric along the boundary to be fixed. That's the fixed physical value of the size of the circle. That's sort of part in response to that question. So this so the actual proper size of this metric fixes the temperature of the theory. Okay, the actual physical temperature. So physical, what we would call physical time, or the time in the boundary theory and so on, is the actual proper time along this circle. Okay. Now, when we do one of these transformations, we can imagine that as, so it's a kind of reparametrization, and it's equivalent to saying that we have now here the boundary is another line with the same proper size that we had here, right? So there's an infinite number of there's an infinite family of lines with the same proper size. Okay. And if the original action had been just this first term, sorry, before I say that, so acting with one of these transformations will transform one of these lines into one of these other lines. Now, the full geometry that we have in the interior is locally is the same in these two cases, but it's actually different because it's the whole shape that we cut out is different, right? So, for example, if here we calculate the two-point function between 2 points that are differ by beta over 2, we'll get something that is constant as we move these 2 points. While here we might get these 2 points, or we might get these other 2 points that are closer, and then we'll get something different for that two-point function. Okay. Yes.
How is that?
Yeah, it's the same. Yeah. So yeah, if you yeah, so when you think about the conformal frame, what you are imagining is that well, we have some proper size that is defined. It's different in the following sense. I'm just fixing the proper metric along the boundary, right? And then you could say, well, I changed my proper metric. So the point is that changing the time or changing the proper metric is the same, right? So in that sense, it is the same. So I could just say that the du, so the metric is just constant. So this is normally we just pick this to be the proper metric along the line. Changing the conformal factor would be here putting an arbitrary function of u, right? Then that's equivalent to redefining this time by you can absorb this factor. I'm choosing this language of I'm choosing here. So in this particular two-dimensional case, it's also related to well, as we said, we can change the factor by doing a reparametrization. That's not something we can do in higher dimensions. And so it's convenient to think of this in terms of the symmetry of changing the time on the boundary. Yeah. The reparametrizing the ADS time. Okay, so the point here is that when you do one of these reparametrizations, you locally is invisible. So if you are a local observer who lives here, you don't notice the difference. But if you have access to longer times, you really notice the difference. Okay. And so Very good. So when we fill the space in with some metric like the ADS2 metric, it breaks these asymptotic symmetries, and it breaks the symmetries to just the SL2R subgroup. So we can still get this circle, and if this circle we displace it inside the whole infinite disk by an SL2R transformation, the circle will still have the same shape. So if you're inside the circle, you do not notice any difference. Okay, so that's the same pattern of symmetry breaking that we had in the SYK discussion. So in the SYK discussion, we had a 2-point function of the fermions, which was SL2R invariant. That 2-point function of the fermions is morally similar to this ADS2 metric. Okay. I'm not saying that I'm giving you a precise map, but it's having the same effect in terms of symmetry breaking. So on the level of just the boundary, we have the reparametrization symmetry. When we fill it in, we just break it. Okay, so this might lead us to expect that also in this case, this action might reduce to the Schwarzian action because we had the same features. And indeed, we can look at that action, and we can analyze it a little more precisely. So we have, I'm going to rewrite it here. The part of the action we're going to be interested in is this term, and we have to remember to add here a term that contains the extrinsic curvature in order to make the variations of the action well defined, to recover properly the equations of motion. So phi b is the boundary value of this dilaton field, and we are going to fix it, and will be part of our boundary conditions, will be to fix this boundary value of the dilaton field. Okay. So we are fixing the boundary value of the metric to have a given proper size, and also we'll fix the boundary value of this dilaton field. Okay. Now, so this is the action, and now we need to do the functional integral, and we can do first the functional integral over phi, and that sets r equal to -2, right? It's like a delta function, and then we just lost this term in the action. So after we do that, we now have to integrate over. Well, this fixes the metric, and now the only degree of freedom that remains is where the boundary is, right? So it's similar to the pictures we were drawing over there. So after integrating out phi, we integrate out g, let's say using the delta function condition, and all we have is some integral, some action, which has the extrinsic curvature along the boundary, and this phi b. Right? So this will be the action for our system, and then we are supposed to integrate over all boundaries. Right? So we see that we get an action for the boundary trajectory, and it's an action which is local in time along that boundary trajectory. And if we generate that boundary trajectory by doing an SL2R, by doing a general reparametrization, then we can think of this action as an integral over some df's divided by the volume of SL2, and then some action, which is an action of f. So and it has again the let me call it phi tilde renormalized times the integral again of the Schwarzian f of u. U is the proper time along the boundary. Okay, rescale proper time, rescale as indicated over there in the last blackboard. So we recover exactly the Schwarzian action. So this is I told you that we expect to get it, but you can just follow the steps I mentioned here and find that you actually do get the Schwarzian action. Right? I guess I'm not giving you the details, but it's sort of a straight some calculation where you parameterize the shape of the trajectory in terms of f, right? And then you get this action. So the point of going through this is to emphasize that nearly this we can call nearly ADS2 gravity or nearly ADS2, and nearly ADS2 has the same pattern of symmetry breaking as the SYK model. So they share with the SYK model that pattern. And because they share that pattern, there are many things that are the same in the two models, right? So for example, the near extremal entropy is always proportional to the temperature. That we mentioned was one result that followed from this action, simple result. And also, if we calculate correlation functions in this geometry, so correlation function will be given by inserting operators here, and then considering geodesics or considering waves that propagate, let's say waves that propagate in ADS2. And so those waves propagate on some fixed background, but then you have the fact that the trajectory of the boundary is subject to fluctuations, which are the fluctuations of the action f. And you can calculate, for example, a 4-point function that is given by waves that propagate between points 1 and 2 and 3 and 4. And there will be a contribution that is particularly large of this 4-point function that will come from integrating over f, right? And that calculation is exactly the same as the calculation we started the lecture with, right? So we'll have to we just calculate first the 2-point function in. So there is a 2-point function we can calculate. I'm going to call it G also. So this is the 2-point function of the fields in the fixed ADS2 background. So this depends on some fields tau1 and tau2, and in principle also rho1 and rho2. So this is the Green's function in the ADS metric. Okay. Of course, it has a simple behavior in rho1 and rho2 because we are somehow close to the boundary, right? Given by the anomalous dimensions. Okay, it has some power law behavior in rho1 and rho2. E to the. There are some factors of delta. Rho1 plus delta rho2. That's the dependence on rho1 and rho2, and then we have some function g hat, sometimes called the renormalized one of tau1 and tau2, which is a power law. In this particular coordinates is a sign of tau1 minus tau2 to the delta. And then when we do a reparametrization, indicated here, so we'll get the factors of f prime from shifting the values of this rho, and then here we insert the reparametrization, and that's the same formula that we were using before, right, for essentially the same reasons. And so we'll also recover the this chaos computation that also gives us the maximal exponent and so on for these reasons. Okay. Yeah.
So in this action, if we just include the matter action and don't include the Jackson type form,
yes.
So will that break the reparameterization as well? How, like, if you just omit the second term and
no,
keep the
no. This one is exactly ADS2 symmetric and will preserve the asymptotic symmetry. So the asymptotic symmetry is a property of your space-time, and if you put matter coupled covariantly to that space-time, it will continue to respect those asymptotic symmetries. So this does not break it. Yeah. So the fact that it's breaking it is basically we add this term, and we fix the boundary condition of the dilaton in this way, and that's why it appears here. So to be a little more precise, just to make this more concrete, so that we have to rescale. So in order to get this action, we have to say that phi b is at this phi tilde renormalized. This stays constant, and then we take epsilon to 0, and that pushes this circle very close to the boundary region. And this whole thing, this whole thing goes to this finite expression. So, well, I mean, this is a standard more or less. This is a more or less standard calculation. So this term, when epsilon goes to 0, this term diverges. This term also diverges, but the divergence is just proportional to the length. We subtract that off, and the thing that is finite is this quantity, which is dependent on f. The divergence is independent of f. Okay. Yes, good. So the difference between the two orders comes when we integrate over f. So this part here is the same as independent of the order. This could be two different fields, right? So these two g's are identical, right? And it's in the integral over the fluctuations of this boundary that we get the difference between the two orders. And let me give a little a nice physical picture for the calculation of the 4-point function again, that is valid for gravity in ADS2. So it's this picture I'm going to give right now is a picture for the gravitational dynamics of the Yakib-Teitel model. So the idea is that so we're in Lorentzian signature. So ADS2 in Lorentzian signature looks like a strip. We can choose various coordinates for this strip. Are you all familiar with this picture of ADS2, or should I? Who wants me to say more words about ADS2? No. Okay, good. So this is the Penrose diagram of ADS2. Those coordinates I had written here, if continued to Lorentzian signature, would cover just this exterior, this region here, this so-called Rindler wedge of ADS2. And it looks like a thermal state from this point of view. And so if we continue the picture, that Euclidean space picture, to Lorentzian signature, so this slice would be a slice that cuts through the middle of that disk. And then the boundary here would follow a trajectory that hits the boundary of ADS at the times here, right? And then we have a boundary on the other side. So the continuation of that gives us a picture for the thermofield double, which contains two boundaries, okay, and so on. And so it will have two Schwarzian actions, one for this boundary and one for that boundary. Okay. Now, and this particular trajectory of the boundary will be a solution to the Schwarzian action. So it's given as a solution of the Schwarzian action. Now imagine that we send in some matter. So I should have drawn this a little bigger. So let me draw it bigger here. So this is the same picture, but I'm going to concentrate on this region. So we had the original trajectory of the boundary. We are taking a scaling limit where this is very close to the boundary, so I'm exaggerating here the distances. Let's say we send in some matter into the interior. Now here, the interactions between the matter, so the matter is, the matter that appears over there. And the interactions between the matter and this boundary particle are SL2R invariant. So in particular, we can think of this as really an actual particle, and this as a momentum-conserving interaction. So the two momentum of this particle and so on are related to the SL2R charges of the system of these particles. And so we can think of this as a momentum-conserving interaction. And in order to understand the dynamics, we see that when a particle goes in, this trajectory gets a little kick, and it gets a kick outwards. And so the new trajectory will go more like that. Okay? So this is the boundary trajectory after we send in some particles. So it's a description of the classical equations that follow from this action, emphasizing the fact that there is this underlying SL2R symmetry, which is the symmetry of ADS2. Let me say first this a little more clearly. So as we notice here, after integrating out phi, there is no bulk gravity term in the action, only a boundary term. So the physics is just the physics of fields and particles moving in exactly ADS2 with no gravity in the bulk, and a boundary particle that somehow responds to, somehow moves, and has its own dynamics. Dynamics given by that extrinsic curvature term. Turns out that that's the same as the dynamics of a particle in an electric field, but we don't need that. So what we need is that it is just some dynamics, right, that is SL2R invariant. So this is a bit like a Randall-Sundrum model, where you have a bulk and a brane, right? This is the UV brane, and we have gravity And all effects of gravity are encoded in the motion of this brane. So for example, I'm now discussing a particular effect which comes from when you send in some matter into a black hole. What do you expect? You expect that the mass of the black hole will increase, and that regions that were the horizon of the black hole somehow moves outwards, in the sense that regions of the space-time that before you send in the matter were visible, now will not be visible anymore. Right? And that shows up here because this boundary, the trajectory of the boundary particle moves out, and now hits the boundary of ADS. It hits the boundary of ADS sort of at an earlier boundary time here, and therefore the horizon is it has moved outward. So this region that before was visible now is not visible. So this is an example of how this dynamics of this particle encodes the gravitational dynamics of the system. Very good. So it's a very simple. So it's a simple story. And then let me go back to the computation of the out-of-time order. Okay. Well, I'm not sure if we're to do that. So so here you have the difference, the distance between these two boundaries is growing exponentially. It doesn't seem in the plot, but here when you send something in, these two start diverging and deviating in an exponential fashion from one another. Okay. But this exponential growth in this particular setup is not something that you can directly see. It's not seen in a simple observable. Like, for example, if you compute an additional 2-point function here, so we have this 2-point function here, and then there is another 2-point function on this trajectory, we'll get essentially a similar answer that does not reflect the exponential growth. Okay. Because of the SL2R invariance of the calculation of these 2-point functions. So in order to make this exponential growth visible, you have to consider this out-of-time order correlator that allows you to have other copies of this contour, and then you can measure the distance between these copies. Okay. And so you can. So for example, you insert some, let's say you have this originally some trajectory here, you insert it, so which was going backwards and forwards in time along, let's say the same trajectory goes backwards and forwards in time, but now here you inserted some operator, so this is the operator you inserted at early times, let's say psi of 0, and so now you'll follow a different trajectory, right? And now you calculate a 2-point function. So yeah. This was one trajectory that was coming back from the future. Now we insert some operator. When we go back to the future, it's at some other position. Okay. That's clear. And here we are going to insert the two other operators, right? The O, let's say the psi. Well, this is the insertion of one of the operators, and then we can insert the other two operators. And we see that now these two insertion points are going to be exponentially distant. Okay, so we'll get that exponential decrease of the full correlator, right? And then, well, then we have that this. So forwards in time, backwards in time, we have the insertion of the other operator, and then forwards in time, and they close, right? And the whole thing has to close by Asymptotic symmetry. So that's the picture, and the exponential deviation is the exponential deviation that we saw here when we kick this boundary trajectory by sending in a particle or acting with an operator. Okay, so I hope that picture is clear, and in this way we can see also some other fun effects, like the fact that that you can make. Yeah, I'm not sure whether to mention this or not. But so you can make wormholes traversable by, as noted by Gao, Jeffries, and Wald. If you have the thermal field double, so we have originally this situation, And then if here you introduce an interaction between these two points, so on in the boundary system, you can think of this as two quantum systems in an entangled state. Yeah, I guess. Are you familiar with that, or should I explain that? Explain. Okay. Good. So I think I'm going to be out of time. Okay. Yeah, that's something a little more basic. So let's think about the trace of e to the minus beta h. So this is in some boundary theory, right? We can think of this as evolution in Euclidean time, right, on a circle. Now imagine that we take this evolution in Euclidean time and we cut here and here, right? And we can now, from here on, move to Lorentzian signature. Right? So that is something. That procedure is something that prepares something called the thermofield double, which is a state that is given by sum over all the energy levels of e to the minus beta en over 2, and then we have the state for one energy level on the right and the CPT conjugate state on the left. Okay, so here we're moving forwards in time, that's why we have this, and here we have essentially the same thing but moving backwards in time, that's why we have this CPT conjugate. So anyway, so we have this thermofield double, and then we can continue this to Lorentzian signature. And well, that will give us some state. So this is an entangled state of two separate systems. Each system has its own Hamiltonian. So there's a Hamiltonian for the so this is in Euclidean signature is this, and then we continue in Lorentzian signature. We have a Hamiltonian which is the same Hamiltonian everywhere, but we should think of this as a right Hamiltonian and a left Hamiltonian. So the two Hamiltonians are identical, but they are acting on two copies of the system. Okay. Okay, so that's the boundary picture. Now, in the bulk, so if the system has a gravity dual, this calculation typically is described by a black hole, Euclidean black hole solution, which has the topology of a disk. And then this procedure of cutting here and going to Lorentzian signature will produce for us this thermofield, this maximally extended black hole that has two exteriors. So this is the exterior, the right exterior, the left exterior, and these two exteriors share this common interior. Okay, so in the Schwarzschild case, this might have singularity here. In these ADS situations, the singularity is more like that. But well, those are some small details. The important point is that we have these two exteriors, and the geometry in the interior is connected. Right? And again, we should think of this as dual to two systems that are defined on these two boundaries. And well, there are things like we cannot send the signal. So if we want to send the signal from here to the right-hand side, we cannot, because we send the signal, it goes into the interior, but it doesn't make it to this exterior region. I should emphasize that so this in these Penrose diagrams and in all the Penrose diagrams I was drawing before, this distance looks finite, but is really an infinite amount of proper time. So this, I didn't say that, but I should have emphasized it. So this curve here has an infinite proper length, and so an infinite amount of proper time. Okay. And so on. So you can well do various things with this. Now, from the point of view of quantum mechanics, no one forbids you from coupling these two systems. So they are decoupled, but you can just say, well, let's just couple the two systems. Let's add an operator, let's say at some time, that some operator that, so we now take the thermofield double, thermofield double. Before we were evolving this with two separate unitary operators, u left and u right, that commuted with each other. They correspond to these two operators. But now, before we do that, let's say we act with an operator e to the o left, o right. Okay, so an operator which is the product of two operators, one on the left, one on the right. And if we think of this as two physical systems living in your lab, let's say a bunch of spins here and a bunch of spins here, no one forbids you from coupling the two operators, the two systems. So, and that leads to an interesting effect. So, come back to this picture. So initially we had the thermophile double that had these two copies, and where the two boundaries were like that. And now we are putting this operator, and it turns out that you can adjust these couplings so that the leading term, the leading effect, comes from the expectation value of the or left or right operator. And that expectation value depends on the location of this boundary. So they depend on this this boundary degrees of freedom. And they give rise to, so if we had an action which contains this expectation value, so the expectation value, as with all these other expectation values we are computing, the leading order is computed by something that is the expectation value in the fixed ADS background, and then we do a reparameterization given by these f's of this of that expectation value, and that corresponds to really looking at the so that has an alternative description by saying that this gives rise to a potential. So this expectation value is a potential between the two boundaries, and if you choose the sign of this coupling constant right, this potential can be attractive. And if this potential is attractive, now the trajectories of these two boundaries will be kicked inwards, and they will look like that. Okay. And so now, if you had sent in a particle here from the left that before was not managing to get to the boundary, now can indeed get to the boundary. Okay. So after we do this, so it makes the wormhole traversable. And now it's not surprising you are sending information from one side to the other, given that you put an interaction. But the interesting thing is that this information is not obviously going through the operator, right? It's not that you're sending this particle and suddenly this particle comes here and it emerges here, and no, it just is going through this wormhole, right? And well, there are a few other things one could say about this, like this is related to teleportation and so on, but I will not emphasize that too much because I guess I kind of run out of time, so maybe I'll just explain that a little bit. So, yeah, the reason one might be interested in understanding this further is that the signal here, so it's going through the wormhole and reaching here with the same somehow shape that you send it in, essentially. So if you send in a bunch of fields that are, let's say, forming that are in some pattern, let's say a message, the message gets exactly undeformed here, perhaps deformed by an SL2R transformation, but that's something relatively simple, to the right-hand side, right? It's not that it has to squeeze to go through this operator and gets completely mangled. It manages to go through quite simply to the other side, and that fact follows essentially from the fact that this whole calculation can be done by thinking about the conformal symmetry and this reparameterization symmetry. So this calculation would have the same value, the same answer, both in ADS2 and in the SYK model, right? In the SYK model, also, if you set up this type of interaction and this type of experiment, you would see the same feature, that if you do some modification here, it will be suddenly then correlated with something here on the right-hand side. Well, the system that no, I mean here we're thinking of the previous evolution up to here, and then from here we have the evolution given by the red curves, right? Let me see. What do you have in mind? I'm not following. Sorry. You come from here. Yes. Yeah. For that, you need to have somehow two traversable wormholes and boost them in some ambient space. Well, I mean, the point here is that we are not joining this into some asymptotically flat space. I mean, if we were to join this into some asymptotically flat space and so on, then this would violate the causality of that asymptotically flat space. I mean, in this space, this interaction that involves these two faraway points, if you only think about this space, this is a very causality violating interaction, right? It's connecting. So you can send some particle here, and it will immediately come out here. But you're only surprised about this if you thought that these two are completely disconnected. But these two, I don't know, could be actually at the same point in some ambient space, right? And then it's not a problem. So, and it's not a problem because it's just simply that this is embedded in a full space-time in such a way that these two are somehow in the same point in that ambient space-time. So this whole discussion of traversability of wormholes being bad and so on arises when the wormhole exists in some ambient space, right? So you have some black hole here and some other black hole here, and they're connected through the wormhole. And if this kind of wormholes were traversable, then you would violate the causality of this ambient space, right? Because it would take shorter to go through the wormhole than going through this ambient space. So, right. Okay. Well, let me. So I'm out of time. So for the next, well, I should summarize. So the what I tried to convey today was to emphasize that both the SYK and nearly ADS2 have the same pattern of symmetries. They realize the conformal symmetry and this nearly scale invariance in the same way. Okay. However, we do not know what the exact dual of SYK model is. Okay. A naive proposal would be to say that we have the dual of SYK would be an action. Well, the Yakif-Teitelbaum action. Well, the action that we wrote over there, plus some matter action here, which involves n fermion fields. So one field per boundary fermion. Now, if you assume that, but that description has some, well, first of all, we don't know whether it's correct or not. So at the level of the two-point function, it might be correct, but at some other levels, it seems to have some problems. It has some problems when we try to calculate the extremal entropy. It has some problems when when we think about the four-point function and its high energy behavior, and its well, some parts of the four-point function that I haven't discussed. So it's not clear, and I think hopefully it will be more clear what exactly the dual is. But another feature that shows, well, there is one feature about this Lyapunov exponent that I have not emphasized too much, is the fact that the Lyapunov exponent goes, so lambda is 2 pi over beta, and then there are corrections that go like 1 over beta j. This is the SYK answer. And this really look like stringy corrections, and so that suggests that the model, well, we can reproduce those corrections. Well, first of all, in any theory of fields, just standard field theory coupled to gravity, we cannot have a correction of this form. Okay. In order to get the correction of this form, one way we can get it using a gravitational-like theory is to have stringy corrections, some corrections due to string theory. And those corrections for a general black hole, let's say a Schwarzschild black hole, they go like 2 pi over beta times 1 minus alpha prime over the size of the black hole squared. the radius of the black hole. In ADS2, this type of corrections are further suppressed by some factor which has to do with the ratio of the extremal entropy and the near extremal entropy. And this factor is, in this case of SYK, is 1 over beta j. So that suggests that in order to match these two formulas, this factor should be roughly of order 1. So that's an argument. And this is a big argument because this formula only makes sense, was only calculated when alpha prime over r squared is very small. But so that suggests some, by string it means something where the bulk theory is known locally in some more fundamental way than just a theory of this form. But well, hopefully it will be understood what the dual is. Let me mention one other thing that I didn't emphasize before that I think it's interesting is this fact that in all the examples of gauge gravity duality that we were usually thinking in string theory are based on very symmetric theories, supersymmetric and very special theories. In SYK we have the opposite, so it's like the generic couplings. Of course it's special because they are couplings of only 4 fermions, but special in that sense, but that 4 fermion coupling is the generic coupling if you impose time reversal symmetry. So there's a symmetry that would make this the generic behavior. And so we have also this feature of random couplings, which we would like to understand more what the role of perhaps random couplings is in gravity in general. So the indications are that this is perhaps not the dual will not be a simple field theory coupled to gravity. It will be more complicated. It will be perhaps some theory of maybe induced gravity, where you have the n fermions and the dynamics of the fermions on that background induces some action for the metric, and this action could be somewhat complicated. But well, I say complicated, but maybe it's simple. So maybe you guys will. Complicated only means people haven't found the answer yet. And an issue that and there are many questions that one would like to understand in this, perhaps using this SYK example, and perhaps most of the issues that I've discussed are issues that involve either almost classical gravity or semi-classical gravity, including gravitational corrections, but they don't involve quantum gravity in the very quantum regime, where you are considering very many 1/n corrections and so on. And at very low temperatures, you might think that the computation of these models are dominated by the Schwarzian action, and indeed there are some limits of the model where this looks like it is the case. And in that case, you can do the quantum mechanics of the Schwarzian action completely, and you get some partition function. I mentioned this before. This was done by full references are in so this calculation is exact in the Schwarzian action, so it comes from doing the Schwarzian path integral, and there's a coefficient that is undetermined, and we know that it should be related to the ground state entropy. And so this result, if you wish, is exact to probably all orders in the 1/n expansion. So certainly it's exact in the Schwarzian theory, but probably the Schwarzian approximation fails for some reason. And it would be nice to understand how to get the correct answer. This answer, we know it's not correct when beta j goes to infinity. So when beta j goes to infinity, this partition function goes to 0, right? That's some power. But the correct partition function of a system with a finite number of degrees of freedom should behave like 1 plus perhaps some correction to the next level, right? And well, in front of this one, there might be a term that goes like e to the beta, right? Like the ground state energy. But certainly the coefficient of the exponential should be 1, not something that is going to 0. So we know this answer is wrong for extremely long beta j's. Certainly for exponentially long beta j's, where we start seeing the discreteness of the spectrum, is wrong. And the question is, how do we recover that discreteness of the spectrum? Because recovering this discreteness of the spectrum from the gravity picture is important for trying to understand what restores unitarity in gravity computations. So all the computations that I've discussed so far are, information is lost. And even in this one, in some sense, information is lost because you go to very long times and you get the wrong answer. And so one activity people have been trying to explore this in various ways is to try to understand how to get those non-perturbative effects. And so they should be here. We see that in this calculation and in many others, we expect that information or unitarity is restored by non-perturbative effects, and we'd like to understand them better. Thank you. Yeah.
Could you give some intuition for why you think that the rule should be something like ADS2 without the
Well, there is at least one person in the audience that there is one person in the audience. Can you raise your hand for Kenta? Yeah. Oh, it's next to you, so maybe he was telling you to ask this question. Who has written a paper saying that we can get some features of the spectrum of some features that I have not discussed, in particular the spectrum. So the model has so when you consider an operator, when you consider this two-point function and you do the operator product expansion, you find here a bunch of operators O(n) that have some anomalous dimensions, delta n, which are not the sum of the anomalous dimensions of these two. They have some non-trivial. There is a non-trivial spectrum here of anomalous dimensions. And it's been suggested that perhaps you could get those by considering a model which has ADS2, and then a circle with some, which is not translation invariant on the circle, but has some kind of delta function interaction potential. And there is a relatively simple setup of a circle, or maybe it's a C2 quotient of the circle, with a delta function potential that reproduces exactly the spectrum of dimensions. So in other words, when you do Kaluza-Klein reduction here, you get a bunch of masses mn squared, so that when you replace the usual formula for the dimensions in terms of the masses in ADS-CFT, you get those dimensions. Okay. Now, there are some details of the proposal that do not, well, at this level it works very nicely. There are some other details that don't quite match, but maybe they might be made to match in some way in the future. And this works for the particular case of q equal to 4. Somebody was telling me that they found a way also to make it work for the other values of q. Yeah, so this is some indication that perhaps, but any theory like this would not give us the correction to the Lyapunov exponent. So any theory that comes from Kaluza-Klein reduction, that is gravity, maybe even with these complications, will not give us the correction to the Lyapunov exponent that we know we have. I didn't mention that this correction can be computed. So there is some number here, it can be computed and was computed. So we computed in the paper with Stanford and myself. So anyway, so it's there, and I think I view it as an indication that it's somewhat stringy, the background that we need to get SYK. Yep.
So is there any hope that this might teach us anything about